Welcome, everyone. Today, we're challenging a fundamental assumption in database architecture with a simple premise: time is not a label. In this presentation, we are going to explore how continuous phase rotation can completely transform temporal knowledge graphs and agentic memory. Let's move to our second slide and look at the static dynamic dilemma in agentic memory. The core problem we face today is that most graph-based memory systems model time simply as discrete metadata, essentially just a timestamp column. This creates a massive dilemma because discrete timestamps treat all relationships exactly the same. For instance, the database cannot mathematically distinguish between a permanent fact, like someone being born in Hawaii in 1961, and an evolving fact, like who holds the office of the US president. The consequence? When temporal conflicts inevitably arise, the underlying large language model receives a poisoned, contradictory context window. As you can see on slide 3, current industry workarounds fail to scale or preserve history. We often see methods like destructive overriding, LLM arbitration, or recency sorting being used. Destructive overriding doesn't preserve historical context, and LLM arbitration fails to scale to millions of facts due to computational cost. The key takeaway here is that recency sorting, which is the most common default, actually silently destroys our foundational knowledge. It does this by burying decades-old, permanent facts beneath fresher, but often irrelevant, noise. To solve this, slide 4 introduces our core insight: internalizing time as a continuous geometric operator. This is actually inspired by cognitive neuroscience, which shows that the mammalian hippocampus encodes time as continuous geometric trajectories, rather than discrete timestamps. Translating this to AI, our system, ROMUM, replaces traditional database timestamping with continuous phase rotation in a complex vector space. The result is that contradictory facts can coexist peacefully in an append-only memory, and conflicts are resolved purely through geometric proximity at the time of the query. Slide 5 introduces ROMUM itself, a drop-in temporal engine for agentic memory. The pipeline consists of 4 distinct phases. First is the semantic speed gate, which analyzes text embeddings to separate static from dynamic facts. Second is an append-only memory structure, ensuring no destructive overriding or expensive LLM calls occur during data ingestion. Phase 3 applies functional continuous phase shifts, or rotation. Finally, Phase 4 is dual-stream retrieval, delivering a mathematically resolved, clean, and ordered output list where the correct temporal fact naturally outranks contradictions. Slide 6 illustrates how this works using the clock hand metaphor. Imagine a clock where time acts as a rotation operator. As our query time sweeps forward, say, moving from the year 2010 to 2026, the most temporally relevant fact mathematically aligns with the relation vector. The profound effect here is that obsolete facts are simply rotated out of phase. The active fact naturally shadows any contradictions, rendering destructive database updates completely obsolete. But what about permanent history? Slide 7 explains our semantic speed gate, which acts as a temporal clutch for the graph. The problem with universal rotation is that if all facts rotate, permanent historical knowledge eventually gets buried. Our solution is to estimate relational volatility directly from text embeddings using this gate. The effect is elegant: static facts, like a birthplace, are given an alpha value of 0 and remain permanently locked in phase. Meanwhile, dynamic facts, like a presidency, rotate rapidly to shadow obsolete contradictions. On slide 8, we dive deeper into how the system learns this relational volatility from semantic space. Because the gate operates on dense text embeddings rather than rigid string IDs, we achieve zero-shot transfer. The system is never explicitly told which relations are time invariant. Instead, it learns volatility gradients through self-supervised pre-training. This allows for incredible linguistic generalization, instantly transferring these temporal physics to linguistic variations and completely unseen relations. Slide 9 shows a real-world application of this geometric shadowing with the crossover trace. Looking at data from the ISU's dataset, we see a highly dynamic relation regarding who Barack Obama was consulting. Around 2009, a geometric crossover occurs. The math realized here means neither fact is deleted. As continuous query time sweeps forward, the phase shift naturally depreciates Tony Blair's relevance while seamlessly raising Xi Jinping's score. This provides a consistently clean context for the LLM. Of course, scaling this is a challenge, which we address on slide 10, preserving MIPS compatibility with the unrotation trick. Applying continuous rotation to millions of vectors at query time would normally destroy compatibility with static MIPS indices, creating a huge scalability bottleneck. Our unrotation trick solves this by exploiting the orthogonal structure of the rotation operator, transferring the temporal transformation strictly to the query vector. The result? We maintain exact temporal retrieval with standard, highly efficient query pre-processing over frozen vector databases. Slide 11 highlights our performance dashboard, proving ROMUM is a state-of-the-art temporal memory. We evaluated across multiple benchmarks. On heavy temporal tasks like multi-TQ, we see a 2 to 3 times improvement in MRR and downstream accuracy. For hybrid reasoning on LocoMO, ROMUM dominates the overall average, excelling in temporal retrieval without degrading open domain tasks. And crucially, on DMR-MSC, we achieve absolute preservation of static general memory. It even achieves state-of-the-art results on pure temporal knowledge graph completion. Let's look at a stress test on slide 12, comparing ROMUM to baselines like HippoRAG. In the multi-TQ challenge, which incrementally ingests 11,000 facts, traditional static systems cluster contradictory facts together, resulting in catastrophic LLM confusion. The ROMUM advantage is clear. By geometrically rotating obsolete facts out of phase, we deliver a clean context window. This cleanly ordered context effectively triples downstream generative LLM accuracy. Slide 13 emphasizes preserving the topological foundation. Forcing temporal physics onto a graph can often degrade standard non-temporal queries, causing catastrophic drift. However, on purely conversational memory baselines with no temporal logic, ROMUM matches or exceeds performance. It perfectly balances dynamic temporal reasoning and pure static memory because the semantic speed gate flawlessly acts as a clutch. It allows temporal physics to assist when needed without destroying the underlying graph topology. Slide 14 explores the synthesis of continuous math and semantic embeddings for zero-shot domain generalization. We tested ROMUM on high-volatility financial contexts that were completely unseen during training. Because ROMUM learns the concept of volatility from text embeddings rather than hard-coded rules, it instantly understands that unseen financial predicates share a semantic signature with general dynamic relations. The result is that ROMUM dominates the financial benchmark without any domain-specific fine-tuning, offering a truly unified, adaptable theory of memory. On slide 15, we outline the 3 modes of inference time retrieval. First is explicit time, where a query specifically asks about a past year, and the engine strictly enforces historical alignment. Second is time-seeking, where the engine evaluates candidates against their own timestamps to answer when an event occurred. Finally, we have time-agnostic, which defaults to now. In this mode, geometric shadowing naturally prioritizes the freshest aligned facts without burying static knowledge. To wrap up on slide 16, the future of agentic memory is continuous. By treating time as geometry, we replace discrete metadata and destructive overriding with continuous phase rotation. Through the semantic speed gate, we achieve zero-shot adaptability between permanent and ephemeral events. This delivers unmatched accuracy improvements while preserving foundational knowledge, all in a drop-in ready, append-only module designed to power the next generation of autonomous agents. Thank you.